Hey guys, we'll talk about the notes for the logarithmic growth section. This is a little bit of a new video, and just so you know, if you hear some weird music in the background, that's because Sadie Water is playing some music in the room right behind me, and he's just blaring it right now. So anyway, in the warm-ups, which is really important to do as far as the rest of these problems down below, we want to write a differential equation for the rate of change of y, so we want dy dt varies jointly with itself and this 5 minus y. So we have some k times y and then 5 minus y. Now this k is some sort of constant and we're not 100% sure what's going on with it, but we still want to create a slope field. And let's say we'll say that k is positive. K is greater than 0 because you kind of need to know that, because otherwise it's going to change things around. So we want a slope field here in the next little part for the equation we wrote in part A. And when you write something as joint variation, it's basically direct variation on more than one thing. So jointly with itself, so with y, and this other chunk. So multiplication between the two of them. Alright, so what do we know about this? We have, I'm going to make this be 0 right here at the bottom. And when is this going to be 0? Well, it'll be 0 at 0. So, and you notice there's no x's in this equation. So all the way across here, I'm going to have horizontal at 0. Actually, let's move, make this a little easier for myself. I'm going to move this up, actually. We're going to put 0 up a little bit because that's a little bit odd. Move you up too. Because you can talk about y as being above 0 or below 0. So let's see what happens to this graph when, well, what's the other value? The other value that's going to make this 0. So if y is 0, this should be 0. But if if y is 5, that will also make this 0. So 1, 2, 3, 4, 5. So we should have two horizontal asymptotes at 0 and 5. Now they're not really going to be quite the same. So let's see here. What happens if y is between 0 and 5? So if y is between 0 and 5, so let's say like 1, I get a positive number because I'm saying k has got to be greater than 0. And 5 minus 1 is 4. So, or sorry, yeah, so it's at 4. So if y is 1, I get like something times something else, but I get a positive number. So everywhere in here, I'm going to get a positive number. And actually, the only way you can get, I got to kind of change this for the notes. Let's give you the k equals 1. I mean, it's important to know which one it is, because in other words, you won't be able to actually sketch these slopes. So if y equals 1, the slope should be 1 times 4 or 4. So at y equals 1, we're getting kind of a steep slope, 4. So all the way along here, we got this slope, right? Kind of try to draw them all the same. And again, there's no axis, so as you go across here, that shouldn't change. Okay, what if y equals 2? So if y equals 2, we're going to get 2 times 5 minus 2, so 2 times 3, which is 6. So even steeper, which is kind of hard to draw. Or you want to know that this is true in your head than anything else. So a steeper graph. So it might even be better to make the first one not as steep, even though 4 is a pretty steep line. The next spot's got to be even steeper. Okay, so let's think here. What happens at y equals 3? You get 3 times, well, 5 minus 3, which is 2. So I get another 6, right? So this is 6 everywhere. So the same steepness. All the way along. But then what happens when y becomes 4? So you get 4 times 5 minus 4, which is 4 times 1, which is back down to 4. So this is, again, not quite as steep. Now, this is not 4 as a slope, but it's not as steep as the last one. So I'm exaggerating the fact, like this is a slope of more like 1 than anything else. But we go from being steep to steeper, and then less steep, and then it goes to 0. So if we picked a point in here, my graph would look something like this. Now what happens if, let's say, y equals 6? Now 5 we already talked about, but if it's 6, what do we get? We get 6 times 5 minus 6, which is 6 times a negative 1, which is negative 6. So as we're above here, we're starting to have a really steep negative slope. And anything that's above this line here, y equals 0, y equals 5, will have a negative slope, because if y is bigger than 5, this chunk will be negative. So if you keep going through this, it's just going to be more and more negative. So it starts at negative 6, but if I use y equals 7, I get 7 times, well, 5 minus 7 would be negative 2, so I get negative 14. It's just going to get bigger and bigger and more steep. So as you go, these are just going to get more steep up until the point where they kind of look vertical. So if your initial value is up here, my graph will look like this. It'll never cross. All right, so where's our third region? We have 3 kind of regions going on here. So if we're above 5, we have this shape. If we're between 0 and 5, we have this shape. Now, you might be able to guess what's going to happen below 0. So let's pick another point. I'm just going to erase, I'm going to erase all of it. Let's steal some of this and give ourselves some room. Does that work? Yeah, there we go. Nice. So let's try y equals negative 1. So what do I get? I get negative 1 times 5 minus a negative 1. So I get my negative 6. And this will actually just basically mirror the top half. So I have a negative steep slope. But as it goes farther, I'm going to get even more negative slopes, which are really hard to draw because 6 is pretty steep to begin with. But basically, anything in here is going to follow this type of pattern. This will look like exponential growth, but like a negative exponential growth, because this is exponential decay. So that's the idea. Like when we make these slope fields, this is what's considered logistic growth. This picture right here. So the idea behind this is you have anything that varies jointly with itself and some other number that will always take the form of logistic growth. And this number right here is called the carrying capacity. So think about, like, if you have a population of humans in a town, but that population can grow kind of at a steady pace, but at some point these people are going to eventually run out of room, and you're going to have to either stop importing people or they will die. Like, there is only a certain amount of people you can fit into a certain area. Think about fish in the fish tank. Your fish tank population might go up, assuming you have both boy and girl fish in the fish tank, and you can ask your biology teacher about that if you want. But eventually they will run out of space and they will no longer be able to breed because they will die off at the same rate as which they're coming in. Either that or the whole thing will tank. But this doesn't usually come from this situation, at least not in this growth version. Now, think about that fish tank. If you put too many people into the fish tank, too many fish in the fish tank, you're going to start dying out. Alright, that music means students are going to start coming, so I will finish this in a little bit.